Hey everyone, welcome back to VLSI Design Verification Professional Training Demo Series. In day one, we covered VLSI ecosystem, what is the design flow, and how do we write a design with utmost care, and what actually synthesis, what is simulation, and all. And also, I told you what exactly the roadmap to become design engineer and design verification engineer. Now let us start day two. In day two, we will be covering what exactly the design is with a small design code, and let's start building a test bench that make you one step closer to become a design verification engineer. Let's add some intelligence to the test bench so that it will be having a checker inside. It will give you the result whether it is pass or fail, and also many things which will be required for debugging. So let's start day two here. So let's continue from there where we left yesterday. Okay. So I have explained what is front end design and what is back end. And remember, in front end, we will be writing the code in Verilog for design, and we will be using Verilog or system Verilog for verification. This we have seen, right? So in the front end VLSI design, if you see here, using Verilog, we will be designing our system. Means we will be using Verilog code to write the hardware. Means your Verilog code will be converted into your Verilog code what we have will be converted into hardware once we synthesize it, but before that we need to verify that properly. Correct? So if we miss some bug in the verification, then that will cause a huge loss to the system, right? So we need to verify the system, we need to verify our design in such a way that we should verify each and every corner cases, and it should never fail, or it should not fail in any circumstances. Okay. So let's say I have given a very simple example yesterday. If it is a 2 is to 1 mux design, we will be having only two inputs and one output, and possible combinations are, let's say if we take AB as inputs and output Y, A can attain 0 or 1 and B can take 0 or 1. So there are only four combinations we are going to get, right? So we need to provide at least all four input combinations and check this 2 is to 1 mux capability. And also there will be a select line here. When this select line is equal to 0, you will be selecting A as your output. When select line is equal to 1, your, let's say, B is your output. So likewise, we will be verifying a design by providing all possible different input cases, right? This is a very simple explanation to verify any simple DUT, let's say, right? So with that intent, we need to write a test bench. So that test bench will generate all possible cases of inputs to that DUT. Okay. So let's look at this example itself. We have a design example here, a 4-bit adder. This is your design block diagram. It says this is a 4-bit adder and the input is 3 down to 0, indicating A will be taking 4 bits as input. B also a 4-bit input. 3 down to 0 mean this is a vector representation in Verilog. If it is a single bit, we need to represent like this, as I shown in 2 is to 1 mux, AB. If it is a vector, we need to represent it as, let's say, 3 down to 0. What exactly this A 3 down to 0 mean? It will give you A of 3, A of 2, A of 1, and A of 0. It means you can provide 4-bit value like this. So this position will be represented as A of 0, this will be A of 1, this will be A of 2, this will be A of 3. It is like that. Okay. So a vector is required here to design a 4-bit adder. So we need to define 3 down to 0. You can see here module adder 4-bit. We have input 3 down to 0A. We have input 3 down to 0B. If there is any carry input required, we will be taking that as single bit. Since in is single bit, you can see here just input scene we are writing. We are not writing any size over here, right? Then we are declaring sum, and also sum should be 3 down to 0, and if carry is the output, cout is taken extra. This also can be a single bit output, right? This is what the declaration inside a module. So these are called ports of your design. These are called ports. Finally, if you bring up an IC for this adder, let's say adder is your IC. In your adder, you will be having input A, it can take 4 bits. Input B, it can take 4 bits. Output will be sum, it will give you 4-bit output. Output will be Cout. This is how an IC look like. It will be having, let's say it may have multiple ports or multiple input lines, similarly multiple output lines, like that. So whatever the module you are going to write, that directly indicate an, let's say, a hardware which is named as adder underscore 4-bit. So this is your design. You have written temp is equal to a plus b plus c in for addition, and assign sum is equal to temp 3 down to 0 you are doing, and cout is equal to temp of 4. A extra bit will be generated out of this adder that will be given to cout. Don't worry about this much now. Let's look at very simple design later and come back to this adder. Now you can look at the verification of this. This is your design. Okay, you will be having a design code like this. So here, after writing a Verilog code, RTL code, we need to simulate it, right? Simulate it. So before we write an actual test bench, what actually designer will do, he will write a very simple test bench and check. Okay, he will write a very simple test bench and check. Okay, then we will be writing a system Verilog or UVM test bench to verify that functionality in detail. That is your functional verification stage. Then after the simulation, you will check for code coverage, and it will give you the result that how much part of your design is covered through the test bench or through the different test cases what you perform. Okay, so that is what the next verification stage is. So in these two stages, you need to write this kind of test bench. See module adder TV. Then you need to declare internal variables here. These are variables, and this is your DUT. This is your DUT instantiated, and then this is where you will be providing all the different set of inputs to your design, right? So you can observe here we have dot a of a, dot b of b, dot scene of scene, dot sum of sum, dot cout of cout. We have provided here. This is the connectivity between the DUT and the test bench we are making here. Dot a is connected to a of test bench variable. Dot b of your design is connecting to, see how actually it look like. This is your DUT. This is DUT. We have written test bench here. Let's say this is my adder underscore TB. Adder underscore TB. I have declared input variable A, input variable B, input variable scene, and sum, and let's say cout. Okay. Your DUT will also be having A, B, scene, and sum and cout. We need to connect this A to A of DUT, B to B of DUT, scene to scene of DUT, sum to sum of DUT, cout to cout of DUT. Correct? That is what we are doing here. This dot A, what we are writing here, corresponds to A of your DUT, and within the braces, we are mentioning this A, comma. We need to connect all the ports to communicate with the test bench. These are the ports of your DUT, and correspondingly we will be having variables here. These variables will be connected to these ports. That is how the communication happen between the test bench and your design. Okay, this will be called as design instantiation or instantiating our design under test. DUT mean design under test. What design we are keeping under test? This design only, right? That's why adder underscore 4-bit is the name of the design. You can see it here. Okay, these are I think you guys have studied already. Okay, let's move on and look at some interesting things. So we have seen the overview of verification plan already. Means the verification flow I explained already. Now let's look at what exactly that verification plan has. You need to set verification plan objectives first. Let's say we are verifying the design functionality as per the specification. This is what your first objective is. You need to follow the specification. Then achieve high test coverage. Let's say the maximum coverage should be 100%. Okay. You need to achieve 100% coverage. Okay. Then find and fix bugs early. That is your objective. Ensure design quality and reliability. You should not change the design. You should just find the bugs and you need to indicate to the designer to keep the quality of the design and reliable. Then sign off the design for tape out or for the next stage, not for tape out to the next stage. This is the verification methodology. First, understand the design specification. There is a document usually. In industry, there will be a design document. You will be provided with design document. By looking at this design document, you will understand what are all the features or the functionalities included in this design. What is the size of, let's say if this adder is your design, in the design spec they will be writing what is the size of A, what is the size of B, what is the size of sum, whether it should take C in, we should take C out or not, like that. All the different features of your design is included in the design document. Then you will be writing a verification document. Okay, test planning, test strategy and test cases. So you will be having verification document here. This is verification doc. In this document, you are going to mention what is my test bench is. Suppose if you are writing a simple test bench, as I said, if this is your TB, you will be putting the DUT here and you say, I will be declaring these signals and I am connecting them with the DUT and I will be having the outputs to be verified here. Remember, your test bench can have a stimulus generator, okay, let's say generator, and here your DUT sits. It will take the input from the generator and it will give the outputs, and internally you may have checker as well. It will check your DUT outputs against the standard outputs. Sorry. Okay, so your test bench will be having a data generator and you have a DUT inside to verify, and then we have a checker as well. Okay. So this is what I am telling. You can have a data generator and it will generate the input values to the DUT, and DUT will be performing its operation. Then you will be having checker inside to check your output. Okay, that is what we will be having in any of the simple test bench. Okay, then that will be added in the verification document. How actually your test bench is, what are all the things you will be adding inside your test bench, that is your test plan, test strategy, and also you will be listing what are all the test cases you are going to write, what are all the different tests you will be performing on your design to verify that. That will be called as test cases. Remember, that is test cases. Okay, then environment development mean the exact test bench. I shown you yesterday the system Verilog test bench that will be having multiple classes, right? So that class-based test environment will be developed once we decide what is my test plan, what is the strategy and the test case I am going to achieve. Then depending on this, you need to start building your environment. Okay. Then obviously test execution and finding the bugs. In this stage, if you see this, in this stage, we will be writing the test bench, okay, in this stage, and we will be also start writing test cases one by one. In your team, you may have some 5-6 members. 5-6 members may be working on different test cases, let's say. Okay, not a single verification guy verifying all the DUT functionality. No, there are multiple people who will be working on different functionalities verification. So these test cases will be written by different people, but they are targeting the same DUT, but different functionalities they will be verifying. Okay. So environment development is test bench writing, then test execution is your actual simulation.
and finding the bug. Okay. Then comes coverage analysis. I said yesterday, coverage analysis mean how much part of your design is exercised during the simulation. Let's say you have, I have also given an analogy that, let's say you are exploring Bangalore. There are, let's say, 20 areas. Suppose you have explored 12, 13. Okay, you have explored 10 areas, let's say. Other 10 areas you can't go, it is very far. Your coverage is 50%, right? If you have covered 15 areas, your coverage is 75%. If you cover 18, 19 areas, then it is 90%. Like that, we will get a matrix in our tool, and you can write a uh, coverage analysis as well. So you will get a result that how much code is executed, and we will be verifying the part of how much part of the DUT is verified. Okay, that is your coverage analysis. Then the different test cases what we are going to perform here, right here, will be executed in a regression. Regression means all the test cases are the different tests what we perform can be run weekly, bi-weekly in a regression run that will take different randomized data every time. So you will check rigorously that in all possible cases whether your test will pass. Okay, it may fail in any one of the regression run. Then you need to catch hold of the bug in that case. Okay, that's why multiple times you will be running the same test case that takes different values every time from the randomizer. So your DUT may fail in some corner cases. For a particular data, your DUT may fail. That will be identified in the regression. Then sign off and reporting is that it is verified. You can take it further for next step. Okay. So that is your verification methodology. What exactly verification environment here? I told you, you need to develop the test bench here in the environment development stage. What you will develop exactly? I have shown one block diagram. See, this is your test bench block diagram. There is a test bench stimulus module. This is your data generator. For an adder, you need to provide A, B, or inputs. Correct? How you will be generating the data? Manually, will you provide A is equal to 0, B is equal to 1? No. So there will be a standard test bench stimulus generator. This is your stimulus generator. That will give the information what it generates to DUT. If your DUT is following some protocol, depending on the protocol, you need to provide the data from the test bench. Then this DUT do its functionality. It will give you sum if it is an adder. There is a checker or scoreboard. This will give you the result that your test case is pass fail. And you can observe here, this is a verification environment. We will be having interface, drivers, monitors, scoreboard, and a reference model inside a scoreboard. This reference model itself give you the expected or the actual value, and you will be check against the result of the DUT. Okay, you can see we have functional coverage and we have code coverage, we have assertion coverage, are the different coverages, and the coverage goal will be, let's say, overall we can target 90%, and actually the 100% coverage we should expect. In some cases, if we cannot cover some particular things, we can waive off and we can say 100%, or we can set a target that only this much I will cover, like that. Okay, we need to plan the coverage as well. And we have directed test bench and test cases and random test cases and corner test cases. Okay, to verify the very basic functionality, let's say. So I have given an example of adder. You can provide a direct test case and directed values that 2 plus 3 is 5. You can provide a direct value and check yes. There is a known value and it is giving the expected result. That is the very basic test you can do. That will be called as directed test. Means you can fix yourself that this is the value I am giving. And let's say very simple inputs. If your design works for that simple inputs, then you can give random values. You can generate 1,000 transactions and check any mismatches are there. Then you can provide corner cases, back-to-back operations. You can stress your DUT. All these are test case development stages. Okay, and these are the test case IDs you can keep for reference. So these are the test strategies and different levels of verification that is not required now. Let's move on to the next stage. Let's look at a very simple code. I have shown a very simple adder, right? Similarly, I have an example here. Let's look at that and verify the adder now. First, let's write a very simple code and let's manually give values, and then let's give some random values. Then let's add a very simple checker to our test bench, and let's automate the checking functionality, and let's have a checker inside the test bench. Okay, that's what our target for today. So basically, I need to start with half adder and full adder first. I think you guys know half adder. Half adder is a device that will add two single bit inputs and generate some one carry. Okay, if you want to design this half adder, you can write a simple Verilog code like this by taking input A and then input B, output sum, output carry. And here we we used assign. Okay, we used assign keyword, right? See here, we have used a keyword called assign. What exactly this assign mean? We are assigning this sum variable, sum output, by calculating A XOR B. That's what it means. Let's assign sum by taking AB into consideration. Let's do an XOR operation between AB. Let's take AB and let's do XOR, and this gives sum. This is what the meaning. Here in Verilog, we will be having different operators to do that. To get a bitwise OR operation, XOR operation, AND operation, we have operators. So this is an XOR operator. Okay. Similarly, again, to get a carry, assign carry is equal to A and B. This is AND operation. It will perform AND between AB values, right? So this will be called as continuous assignment. Remember, it is called as continuous assignment. Means whenever you change the value of AB, these two lines are going to be executed. There is no condition for these two lines to execute. Just give AB through these inputs, you will get sum and carry immediately. So remember, if you write anything with assign keyword, they will execute immediately. Okay, those are the lines which will execute first in your Verilog. You need to understand Verilog scheduling semantics. Okay, in Verilog scheduling semantics, there are 4 stages. Okay, scheduling semantics mean which are the things execute first, which are the things execute in the next stage, let's say. So we will be having 4 such stages. One is, the very first stage is active, means all the active statements will execute first. One of those active statements is assign statements. This is first thing will execute. In the second one is inactive statements will execute. First active statements means, let's say, assign keyword statements, and anything you have used gate primitives, let's say AND gate directly used, OR gate directly used, NOT gate directly used, all those will execute first. Then if you use $display to display something in console, that will execute first. I am talking about in a single timestamp, let's say at 0 nanoseconds, at the very early stage of your simulation. Okay, this is how the flow will be. In your Verilog code, if you use assign statement, that will execute. If you use AND gate primitive, let's say, other than writing like this, assign sum is equal to A XOR B, carry is equal to A and B, we can use an AND gate by calling AND. You can provide some instance name, and you can give carry is my output of this, and A comma B are my inputs. This is your gate primitive AND gate. This is having standard implementation inside a library. That AND gate will be called. And these things will execute first. That is active mean. Okay. Then inactive statements will execute. Inactive in the sense, suppose if you have some statements written with #0. Hash 0, hash mean in Verilog, remember, hash mean delay. If you want to provide some delay, then you can use hash. Suppose if hash 0 is written, that is the next statement executes after active. Okay, and also blocking assignments. Blocking assignments will execute in the active region. Hash 0 with blocking assignments will be executed in inactive region. Then NBA region, non-blocking assignment region. Non-blocking assignment region. Do you know what is blocking assignment or non-blocking assignment? Can you comment in the chat if you know blocking and non-blocking assignment simply? If you use, let's say, y is equal to a plus b, this equal operator is a blocking assignment. Suppose if you use y less than equal operator for a plus b, this is a non-blocking assignment operator. Okay, all these things we need to understand while discussing Verilog. These are very, very important for the designer. Okay, not only for the designer, also for the verification engineer who is using these, has to know how exactly I'm supposed to use that. Okay, all non-blocking statements what you are going to write will execute parallelly, but the blocking assignments, if you write one after the other, that will execute sequentially. Okay, all these things are very, very important in Verilog. Okay, so those will execute in third stage, means in 0 nanoseconds itself. For you it is 0 nanoseconds. For your simulator, 0 nanoseconds is subdivided like this. It is executing active statements first, then it will execute inactive statements, then only it will update the NBA statements, then it will update the monitor statements, like that. Do you know for alternatively for dollar display we have dollar monitor also? In the fourth region, let's say that is monitor region, we execute dollar monitor things. We predominantly use dollar display, dollar monitor in our test benches. Okay, so dollar display will execute in active region itself, but dollar monitor will execute at last. It will keep on checking the change in the input and outputs, and it will display. Okay, so let's look at all these in some examples later. Now let's jump on to the next thing. So this is your very simple half adder design. Similarly, we can write a full adder design. Okay, A, B and C in. If your third input comes, then you need to call it as a full adder. It will take the third input also. Okay, it takes two single bit inputs along with a carry input from the previous block. That is full adder. Sum and carry will be the output. Here also the sum will be generated by XORing A, B and C in, and carry will be generated by A and B. This is one AND gate. B and C, this is another AND gate. C and A, this is another AND gate. Okay, one single XOR gate can generate a sum A, B, C in. But one AND gate, one more AND gate and one more AND gate with an OR gate can generate carry A, B seen and A seen. Okay, this will provide you the carry. The same expression we have implemented here. We can write it as A dot B plus B dot seen, then plus seen dot A. That is what we write here. Carry is equal to, right? So if you have an expression like this for your design functionality, you can directly go with assign. That is what it is. Okay, this will be called as data flow description. If you remember, we have different descriptions in Verilog. We have gate level description, gate level. What do you mean by gate level? You will be using gate primitives. Okay, gate primitives. I have shown AND gate, OR gate, NOT, NOR, XOR. Directly you can use them. Okay, NAND, NOR. So in your library, Verilog library, all these implementations are there. Directly you can use an AND gate if you want an AND gate functionality for any simple inputs, and A1 provide output Y, any variable of any variable with let's say variable y here and a b inputs. So the rule is first you need to provide output, then we need to provide inputs. These are gate primitives, gate level description if you use them directly. Then we have data flow description. Data flow description. Data flow description means you will be using expressions there. Expressions. What expressions? These Boolean expressions. For some, it is A XOR B XOR C, right? Similarly, carry is this, right? The same kind of expression will be used in data flow description code. Then we have behavioral description. Behavioral description. In behavioral description, you will be using advanced Verilog constructs. Let's say condition to be checked and we need to execute the things. If condition can be used, for loops can be used, always block can be used. Then we can use any other advanced constructs. Let's say tasks can be written, functions can be written. So all these comes into picture when you are implementing your design in a behavioral level. Behavioral level mean how the behavior of your design is, that you will be writing as a code. You will not worried much about how many gates it will take, what is the operator it will take, how the internal functionality will be, how the gate level structure look like. You will not worry about all these. In a behavioral description, you will be writing the code just to satisfy the functionality. Let's synthesizer will decide what hardware it should provide. But while using them, you should know what hardware it is going to get. It is going to generate, right? That is how you will be writing a design code. These are very simple codes where a data flow description can be used. Why? Because we know the functionality already. We know the expression already. If you know the expression, if you know how many gates required and how actually that will be, then you can directly use an expression. Suppose if you are designing some adder, you need to use a plus b. Y is equal to a plus b only. You can't go and write each and every gates required for this adder, right? That is what we call it as data flow description. Now let's come back to the actual thing. Let us write a adder design code. This is your adder design code. And let us write a simple test bench. I will explain you, and let's simulate in EDA Playground today. Okay, let's give you a kind of clarity that how actually the test bench will be written, how simulation will be done, and how actually we'll be looking at the waveform like that. Okay. See, this is your adder design. First, let me write a block diagram for the adder, what we are designing here. This is adder. We are just taking AB. We are not taking any carry, anything. We are designing a 4-bit adder. This is 4-bit. Okay, 4-bit adder. 4-bit adder will be taking 4-bit as input A, 4-bit as input B. And I will be generating the sum. This sum, let also declare it as 4 bits. Okay, let's assume it will generate a 4-bit output. So in this case, we need to have a logic in such a way that we should get a sum. Okay, by just adding A plus B. This is what my simple design is. Now this is your project. You need to verify this. Anyhow, a designer has written this code. A is there, B is there, sum is there. In the document, we have given that A should be 4 bits, B should be 4 bits, sum should be 4 bits. Okay, and we have used some functionality to get the result. Now you will be writing a test bench. The very first thing you will be doing is you will be generating the block diagram. Okay, this is your module TB. The name of the module is, let's say, TB. And here I will be using variables called reg A, reg B, and reg sum. And I have instantiated my DUT here. DUT also has A, DUT also has B, and DUT is forwarding back sum. Let us connect them like this. Okay, this sum. So this instantiation we are doing here, this is your DUT. DUT as A, this is your DUT signal. Remember this, many people don't understand this, simply they will write. The very first variable we are writing here is a DUT port. You need to use the name exactly, A. And the second variable within the braces you are writing is your test bench variable to connect this A, to generate a signal from A, and you need to pass it to the port, right? So you are connecting here. Similarly, B to B, sum to sum. Okay, you did it here. Okay. Then as soon as you instantiate your test bench, you should start generating the input for them, input for the DUT. So in Verilog, remember, if you want to write any simple thing, let's say A is equal to 1, you need to write in a procedural block. You need to use initial. Okay. Let's understand later why initial is used, when always will be used. Okay. How, when actually clock will come, how to handle clock, how to generate clock, all those are become a part of the test bench in your sequential circuits. Let's understand that later. Now remember, you need to start providing values under initial. So if you want to provide A is equal to 1, I said initial A is equal to 1. Like this you need to provide. So now we have B also. We need to provide B also as 1. Then you need to put these two under begin end. You need to group them together under one initial block. So now it becomes initial begin A is equal to 1, B is equal to 1. That is what we are doing here. Initial begin. Let's look at monitor later. We are providing the value for A. What is the value of A we are providing? A is 2. Why it is 4 tick D2? This 4 is the number of bits the simulator should take out of this for A. In binary, it is 4 bits. So I am providing a value called 2. This 2 I am writing here is of type decimal. Okay, 4-bit decimal. It is 4-bit in binary, but here I am providing a decimal value. So this D I am using. Suppose if I need to provide the values in binary only, then I will write 4 tick B. For 2 it is 0, 0, 1, 0. Correct? So like this you need to provide the binary value. Starting from 0, 0, 0, 0 if you want to provide 0, 0, 0, 0, 1 if you want to provide 1. This is decimal 0, decimal 1, decimal 2 is 0, 0, 1, 0, and 3 is 0, 0, 1, 1. Like this you can provide till 15. 15 means 1, 1, 1, 1. So there are different possible values for A, B, or A can go from 0 to 15 and B can go from 0 to 15. Right? All these are different possible values we can provide. Now, in our case, we are providing A is equal to 2, A is equal to 2, and we are providing B is equal to 3, and we are expecting sum should be 5. Then only my result is correct. That is our first value, first set of value. Second set of value is we are providing A is equal to 4 and B is equal to 1, and we are expecting sum is equal to 5. Then we are providing A is equal to 7 in the third case and B is equal to 0. Then you are expecting sum is equal to 7. Then these values comes as output. Your DUT is correct. So to provide these values one after the other, this is at 0 nanoseconds. Then I need to provide some delay before the simulator takes the next value, right? That's why I have added #10 here. This is the delay. So it is like A is equal to 2 will go, B is equal to 3 will go from 0 nanoseconds to 10 nanoseconds. Those are the values. Then 10 nanoseconds to 20 nanoseconds, the next set of value, A is equal to 4 and B is equal to 1 I am providing. Then from 10, 20, then 30, A is equal to 0, 7 and B is equal to 0 I am providing. This is how you need to look the waveform. You should know at what time I am providing what values, correct? So if you are having multiple set of values like this one after the other, it is very difficult to look at the log. That's why we added this monitor statement here. What this monitor statement will do, it will pick the value of A, B and sum and it will put it here in binary. Sorry, in decimal, D, in decimal, in decimal. Okay. This A will come here, this B will come here and this sum will come here. And whatever we are writing with the double quote, this is a string. A is percentage %D, and if you write A here, and then B is percentage B, and if you write B here, so this A will come and sit here. Once it simulates, B will come and sit here. You will see the log, right? A is 1, B is 5, something like this. Okay. So that is how a very simple design and test bench will be written. Now let me take you to a simulator directly. The same code I have added here. Okay. You can just look at how to use EDA Playground as well with this example. And also you can look at how we will be seeing the waveform. Okay. Let's look at that. I will be sharing a different screen. Once again. Your design. What is the design we have? Just sum is equal to A plus B. Okay. Okay. Before doing this exercise, let me ask you something. How many of you used EDA Playground? Just comment yes or no. How many of you used EDA Playground? Okay, Siddharth HK used, Shashank used, Jyoti used, Shweta used. What about others? Durgesh used Multisim also. Okay, Kulsum is not used, but he used Vivado. Okay. Others, what about others? Have you used EDA Playground anytime during your simple Verilog design and simulation? Yes, Deepa also says yes. Yes. See, I said already, this EDA Playground is a very handy tool. You can simply write your code, design code here, and you can write some 10 lines of test bench code here, and you can verify your DUT then and there itself. There is no need of any particular tool inside your system to check this design whether it is working fine. You are trying out something very simple design, and you don't want to spend much time on that to verify it. Let's say directly use this EDA Playground and simulate. If you want to use a tool, then you need to invoke it, and then you need to provide these things, and you need to save that file. Everything is taking much time. So we can use EDA Playground for simple designs, and there will be many example codes to understand the system Verilog concepts, let's say. In such cases, every time going and working in a tool is bit hectic. Okay, directly you can come here and use this EDA Playground. It will give the same results of as your tool gives. Okay, basic things. See, this is your test bench area. You can write test bench code here. This is your design area. You can write the design code here. Okay, at the left side, you can see there are different simulators available. I have selected this, and I have provided the time information as I am providing the values here as in nanoseconds, 1 nanosecond, like that. Okay, so because of this monitor statement added here, we can see the different values printed. See here, these are the three values we have provided, correct? We have provided A is equal to 2, B is equal to 3, then sum is 5, right? Is that the right value? A is equal to 4, B is equal to 1, giving 5. A is equal to 7, B is equal to 0, giving 7. Yes. So this is how you can verify your design by looking at the log. No need to no need to go and look at the waveform. Okay. Every time no need to go in the waveform and check. You can add more statements like this, and you can get what exactly happening inside the test bench. Okay. And also we are taking sum from the DUT only, right? This sum is generating here. Nowhere in the test bench we have added A plus B. We are getting sum from this variable inside the test bench, and now we are printing that in this monitor statement, correct? So this is how we can use it. And also if you want to get a waveform, then click on EP wave after run. Okay, save this and run again. Okay, if you have not added the waveform generation things, let's say dump file is required, so you need to add these two lines. Okay, it will also throw you error. If you just go and check that, you will come to know what is missing. You can add it here inside in the test bench. You can put it under initial begin and end. Okay, I have added the dump.vcd now. So now we can look at the waveform. It will generate the waveform as well. Yes, Shweta, you're correct. Dump file is used to get the waveform. So what are those values generated for sum and A and B? All are dumped in a format to display the waveform in a dump file. So that will be used here to display. So this is your waveform now. A, B and sum you can see. You can observe here, this is TB signal, TB bar sum. Okay, TB bar A, TB bar B. Now if you look at A, B and sum of the next three values or next three variables, these are from DUT. So you can also verify here that what is your DUT output, whether the same thing we are observing in the test bench also, or there are any changes happened in during the test bench, or we are getting the exact values in the correct timeline. This is the timeline 0, 10, 20, and we have 30 here. Okay, so this is your waveform. Like this also you can check your results if you want to know from the waveform. So remember one thing, we will check the values here only, and if it is correct, it is fine. Otherwise, you need to go to the waveform and check any particular signal is triggered or not triggered, or working fine or not, like that. Okay. You are thinking like this design is working fine. How many of you say this design is working fine? We have checked with these three cases and the design is absolutely correct. Can you comment? Can you put a message here? Is this design correct? Working fine? Can we say this design is working perfectly? Many of you are saying yes, it is correct, like that. Okay. So what is happening here? Okay, Jyoti Sri Hiremat saying no. Why Jyoti? Why it is not correct? Can you speak? Or you can put a message. You can. Some should be one bit extra. Exactly. That is what we are missing here in this case. Some should be one bit extra. We are taking 3 down to 0. It will fail if you provide a bigger value for AB. If you provide bigger value for A and B, okay, your sum will generate wrongly. Okay, I will just stop sharing this and I will share here in this example is that see the same DUT. Okay, we verified this DUT by providing small values and you guys said yes, it is working fine, but this is not exactly working fine. This provides wrong results if you increase the values of AB. That is why to provide AB randomly, we need some randomized data generation. Okay. See here, the TB looks like this. AB sum, and this is your DUT instance. I just added pass fail as two variables here, extra. I have added expected variable here. Screen is not visible. So here we added a 4 down to 0 expected as a variable. See, this is done by designer. Now you can think like, this code is a designer code. He made a mistake that he took 3 down to 0 sum here. Okay, but this will give you the correct results for small values of AB. It can generate maximum value of 15 as sum. Okay, if you provide 10 and 6 from AB, 16 will not generate it here. Why? Because sum will be restricted to 15. We are supposed to take it as 4, but designer has provided 3 down to 0. We need to find out that bug. But in our previous case, because of very small values we are providing for AB, we couldn't find that result, couldn't find that bug itself, right? So we need some random value generation. See here in these two lines, I am using some random value generator. These two are Verilog constructs, $u random. I am providing a range of 0 to 15 values you should generate for A and for B. $u random range will generate random value, random unsigned value. This U indicating unsigned. If you just choose random, it will generate signed value. Okay, now it is generating unsigned value. And I know as a verification engineer, the expected value should be declared with size 4 down to 0. 1 bit extra is required. So I have an expectation here. I need to have a logic to calculate a plus b and I should get it in expected value. Okay, for that I am calculating a plus b again and taking in expected inside a test bench. This is your expected correct output generator. This never fails. Not only a plus b, you can use any other logic to satisfy your a plus b to generate sum. This is your expected value. Now I am checking the sum what it provides, what DUT provides will be correct or not against expected value what we calculated here inside test bench. Okay. Now if your design is correct, the sum what we are going to generate here will be equal to expected value. If this sum is not correct, it will be an fail case. So when it is correct, we are incrementing pass, and when it is failed, when it is not correct, we are incrementing fail. We declared two variables here, right? Fail is equal to 0, pass is equal to 0. So depending on the number of test cases we perform, this sum and fail will generate the result. See here, I am repeating these things 50 times. Means 50 different cases of inputs I am providing. So only 3 cases we have provided in the last example. That is not sufficient. Okay, that may leads to wrong conclusion. Small values we provided, that is called as directed test case. Here we are providing some random values. Okay, 50 times we are repeating this using repeat block. Now expected is equal to a plus b. This is checked against the sum generated by the DUT. If it is pass, pass is equal to pass plus 1, or you can use it as pass plus plus, otherwise fail. And also I am displaying what is the percentage of pass and fail, not the percentage, what exactly the number of pass and number of fail. Let me run this code and see the results now. We have a monitor statement anyhow. We will see all different 50 values what it generates, and also it will print sum. Okay, and we are not printing expected value, we are printing expected value only when it is failed. Okay, now let's observe the result. See here, these are the all 50 cases. The very first thing is it is printing starting random test. That is what we have added here, starting random test. Okay, see, this is the difference you're going to see. Monitor statement is the first line inside initial block. Display statement is the second line. But you are seeing this display first, starting random test. Due to this monitor, you are getting this output here. Means it is executing late. This is what a Verilog scheduling semantic do. First, it will execute display, which are all the displays you have in this timeline. Then, if monitor is there, that will execute at the last in that particular timeline. Okay, that's why monitor pick all the changes of a, b, sum, and all other variables what you are updating inside a test bench, and it will display correctly. If you use display statement in place of monitor, you may not see all the values correctly. That will execute before you randomizing the values, right? So all these things we need to understand with some proper examples, and we will be doing that in further sessions. So now you used random values. So yeah, we are seeing A is 3, B is 15. We are supposed to get 18. 15 plus 3 is 18. We are getting 2. Why? Because your DUT is supported only 4-bit output. We need 1 bit extra. So this is wrong. So it is failed. 0 plus 10 is 10. Now it is correct. For this input also it is correct. 14 plus 12 is wrong. So you are getting fail case here. So by looking at these in your log, you will come to know, oh, you got a failure. Fail will be printed in your log. We call it as log, simulation log. There will be a simulation file, log file. You can download these files after run also. You can get an output text file, and you can also run through some do file. All those are available in the EDA Playground. So once you get that file, if you open that and see how many number of fails and how many number of passes are there, you need to go down and check that first. Oh, there are 34 pass cases and 16 number of failures. In the previous directed test case, we have never seen this, correct? Right? Suppose if we conclude there itself that, oh, it is working fine, My adder is working fine for simple cases. 5 plus 3 is equal to 8. And if you move forward, then this will fail for at least half of your inputs. Correct? That's why this kind of intelligence is required in your test bench to identify bugs. This small change is required here, but your test bench indicate that failure, how many times it may fail, right? So we added a simple checker here. This is very simple checker. This part is very simple checker. This kind of checker we need to add inside a scoreboard in a real system Verilog DUT. That will provide you the results in more precise manner. Similarly like this, but in more precise manner. If you use UVM for this, it will give you more information in your log so that you can identify which line it is failing also. Okay. So this is about a simple adder design and how we can verify it, and how a simple test bench if you write that may violate the things, and it may miss out the bugs. Okay, this is a very good example to understand how your test bench, how strong your test bench should be, and what's the use of randomization. Now if you just change it to 4, let me fix it now. Change it to 4. I'm changing it to 4 down to 0. Now if you save it, execute again, you should not get any failures now. It will support 5 down to 0, means a 4 bit input will be added, and finally it will generate 5 bit out. But still it is failing. Why? Because here also you need to change that sum to 5 bits, right? 4 down to 0. So these kind of exercises you need to do at your learning stage. You need to modify the code, you need to run multiple things. See here, 50 times it is passing now. Now your test bench is giving the correct pass result as 50, fail result as 0. It means your 50 test case is working fine. If you want to run multiple times, if you want, let's say, if you want to run it for 100 times, you can do that. Okay. Let's just look at what happens when we run 100 test cases. See here, 100 times it is passing. All the results you are going to see here. There is no failure. That's why we are not seeing any fail output here. Everything is passed. Okay. So I will give you this code. If you want to try out something on this, you can keep this code with you. Just put it in a browser. It will open and you can run it. You can click on save. Okay. And you can save it in your playground area. And if you want to use that in any time, you can go back and edit. That is the advantage of VDA Playground. We have seen a very simple test bench added with some intelligence, and that gives fail and pass cases. You can implement this for any of the design. You can try out it today. If you don't get the result properly, you can come back to me. I will give you the solution. Okay. Take any other design. Let's say try it for multiplexer, try it for encoder. But you need to add a checker inside your test bench which should match to the logic of your design. The same functionality you need to mimic here in different way. Okay, that is what exactly the checker is inside the test bench. Okay, you can try out something like that and come back to the next session. Let's discuss more about this randomization. In the next session, we will be doing a class-based test bench. Let's write a simple class for this. Okay, and let's see how actually that class-based test bench behaves and what is the advantage of having class over this module level test bench. Okay, that we can do tomorrow. We can stop here, and if you have any questions you can ask me. I will be here for another 5 minutes. Have you wrote these kind of checkers inside the test bench and tried simulating? Hello? Okay. How to write pass fail in the test bench? Please look at the code what I have provided. I have provided the link here, right? You can just take that and you can look at that code. If you didn't get, if you don't understand properly, again come back to me, I will help you. Okay, I have added a simple checker here, right? Pass fail we have declared as int, and a plus b we have taken for expected, and we are checking expected against the sum it is generated, and that is giving pass fail result, right? You just go through each and every lines in the test bench once, and if you didn't get, please ping me, let's connect. Okay, so everyone do the same thing, do this exercise today, and let's connect again tomorrow. Tomorrow let's see a very simple class based test bench and simulate it, and after, let's say tomorrow, from the next day onwards, from the, let's say, fourth session, let's start digital. From there onwards, let's go as per our syllabus. Now I am giving you the gist that how actually the verification will be from very basics. This is very basic.